Nothing becomes more important just because you can measure it. It becomes more measurable, that's all. This is William Edwards Deming. Indeed, measuring continuous change will at best be approximation. And we can get better and better approximations of change in a changing quantity at any instant. What Deming said about measurement is quite at the heart of calculus. We will the same discover as we go along. To understand change, we have to measure it. Thus, to know our world, natural and engineered, we measure and decode the changes it lives. What is measurement of change? How it is expressed? Mathematically, change is simply the difference amount of post and pre-change quantities. By itself, change is a simple mathematical computation. To be frank, it is more of how we express that difference, and what does the difference express, quantify. This difference could be expressed as absolute or relative, exact amount of change or ratio of change to the previous state of measure. The relative change, expressed as ratio or percentage, is more enriching, tells us more about the change. For example, assume something changes by 10 units, absolute measure of change will be 10 units. But the relative measure may wildly vary. For instance, relative change could be 1%, that is 10 by 1000, or 200%, that is 10 by 2. This is a relative measure and intrinsic, it is change in its own terms. Even more insightful would be to know a change that it is expressed in extrinsic terms, such as 5 units per hour, 1 unit per hour, 0.1 unit per kilogram, 0.05 unit per degree rise in temperature, and so on. This is the rate of change, the pace of change. Why measure rate of change of a change? What is the one measure of change that says the most about all kinds of change? The rate or pace of change. Rate is the meaningful, monetizable, and immeasurable yet characteristic steps in the quantum of change. Why pace is so singularly important? Quite a few reasons. Pace shows the significant, opportunistic relationships among quantities. For example, low rate of change with respect to a quantity means less relevance of that quantity to the changing quantity. Knowing pace helps define the limits, impacts, actions, risks, etc. Of change, for example, the circuit breaker is a response to unacceptable rise in current levels in a very small window of time. It helps save loss, money. As we will discover soon, pace is a derived quantity, not directly measurable. It opens up a world of more incisive and valuable insights into any change. For example, speed and acceleration of any motion are about nuances of pace of the motion. By the way, let it be reminded that speedometers do not read or measure speed directly from the motion of a vehicle. It measures distance traveled and time, and flashes the speed, computed from the distance and time measures. The distance measurement is done through the number of rotations of the wheel in a given time. Rate of change is the singularly valued measure of continuous change. The measurement of rate of change is much more demanding for continuous change than for discrete change, for a continuous change is constant only over a very small period of time or any other conditions, and that is a tough measurement challenge of change. But make no mistake, we can only measure continuous change in those very small periods of time or other conditions, for only in such fractional moments can we get a singular value of the change. There is also the challenge of history in continuous change. There is far higher chance of patterns in continuous change. For example, over a longer period of something in motion, we can see relationship between acceleration and speed, even direction, and that is a pattern. Patterns have predictive powers, and that is true in many continuous change situations. In continuous change, the only way to measure the gross change, that is, the quantity of change over a period, is to add up the very small changes. Importantly, the rate of change is also the absolute quantum of change. In that small amount of time or any other variable, if the entire change is split up in the same intervals of change. Measuring continuous change is an imperative, because discrete reading or measurement could turn out to be disastrous for continuously changing thing. For example, a big momentary spike in current can blow up a circuit, and the devices connected in it. Continuous change implies the use of non-physical indirect measures, that is, mathematical or analytical methods. Mathematical is also called analytical because we analyze a situation and create an equation or function of the relationships at work. We then use that function as a proxy for the real relationship in action and see the change as it happens. Rate of change is also a relevant measure for discrete change. Pace of discrete change is mostly direct and discernible. The steps are discrete and episodic. Calculation of pace is rather straightforward and precise. It is the quantum of the steps. Also, there is less relevance of the relationships of discrete changes to other quantities. It is more about the nature of each step, and there is less of overall story. Also, there is less relevance of the relationships of discrete changes to other quantities. It is more about the nature of each step, and there is less of overall story. For example, many of the economic events and government policies and actions are periodic changes. The changes do not bear very close relationship to specific conditions. But it does not mean they are less important, just that their computation is easier, simpler, and mathematically no new tools and concepts are needed. We would not pursue discussion on discrete changes because no special mathematical tools and concepts are needed to measure and evaluate such changes. Analytically measuring continuous change. Let us go back to the basics about analytical measurements. The most characteristic feature of analytical, theoretical, or mathematical measurement of quantities is that such quantities are physically or directly immeasurable, such as speed and pressure. Analytically determined quantities are derived from physically measurable quantities or other analytical quantities. For example, speed is mathematically derived from distance and time, and acceleration is derived from speed and direction. The way we mathematically derive is to create equations for the change in the form of functions and work on the functions. These are detailed next. If it helps in appreciating the commonness of analytical quantities, let it be known that even addition, division, etc. are analytically computed count of quantities. Counting and measurement are the primary means of quantification. All of mathematics is built on the two. Operations and beyond is, in a way, analytical means of quantification. Continuous change may be fast or slow, but we would not know if there a change till we measure it at various instants. There is no other way to detect continuous change. This is also why instantaneous rate of change is the way to know continuous change. We next explore motion, the simplest and the most common experience of continuous change. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.